Welcome back to another calculus video. In the last section, or the last lesson, we learned about integration or anti-differentiation. We're gonna use this to our advantage when understanding graphs of functions. Now, before we do the crazy stuff, we are gonna have to look at this idea of area under a curve, but I'll tell you that later. So we have these techniques. We have the simple power rule, and we just have our trig integrals. And you might be wondering at this point, well, why can't I have the integral of secant x dx? Why can't I have that one? Well, you won't actually get that later. You won't get it until Calc 2. And a lot of teachers divide the sections, or the calculus sections. I personally like to divide it like my first teacher did. And it's taking all the integration rules, putting it at Calc 2, having all the applications and first impressions or techniques right on the first calculus class. And that leaves more for Calc 2. So we're going to discuss a technique later on called substitution. That will help us integrate more stuff. But all we have right now is just my simple power rule and integration. And we have the trig integrals. So if I were to give you the integral of x over root x dx, you can do that. You can turn this into x times x to the negative 1/2. Add the exponent, and you get the integral of x to the 1/2 dx. This is, of course, you add 1, you divide by 2. So, or divide by thing, you put a plus c. Let's check that's right. Okay, so that gives us our answer, and yeah, we can do it. But there's some integrals that we cannot do, such as, well, we can do the integral of sine x, right? What is that? That's negative cosine x. Well, we can't do the integral of sine of 2x. We cannot do that right now, at the moment. The answer, if you're wondering, is going to be 1/2 sine 2x plus, if you're wondering. But today, we're going to learn that method. We're going to learn the method of, well, substitution, right? Because there's some functions that have an easy composition. So if I were to tell you, what is the derivative of a composition? What is the derivative of f of g of x? What is that? Well, that is f prime of g of x times g prime of x. Interesting, huh? Well, if we integrate both sides, or take the antiderivative, what happens is you cancel. The antiderivative undoes the derivative. It gets back your function. So you're left with f of g of x equals the integral of f prime of g of x times g prime of x dx. That is your u substitution. Kind of. It is not really. You're gonna let your u substitution is your way of getting here. But if you recognize this pattern, that hey, if you have a composition, if you have an integral with this form, well, you know the integral, it's just that times the composition. And I'll tell you how to get here using substitution. So let's do an example. So here's an example. Let's do the integral of cosine 3x. We cannot do that right now because it doesn't fit our forms. Sure, it's a trig function, but it's not cosine of x. So we can't do that. Well, let's give a little partial. Now I'm going to add something special here, and you'll see why. So when we evaluate the integral of cosine 3x dx, we'll save it for later. I'm going to do an easier one, and I'll tell you why. Evaluate the integral of 3 cosine 3x dx. That one is easier than this one. We'll see why. So let's just temper. Whoa, can you identify a composition? First of all. If you can, that's great. So let's make the substitution. Do we recognize a composition of functions? Can we recognize at least this? Can we recognize a composition? Right now it is right here, f prime of g of x. But if we can recognize this portion, that's great. So we can recognize this portion. Well, g of x is just 3x, right? This is the cosine. So the easy way to do this is, hey, I see a composition of functions, 3x and the cosine x. Well, what if we let the inside equal u? If we let the inside equal u, let's take a derivative of both sides. So du dx equals 3. The derivative of u with respect to x equals 3. Let's put that in a differential form. Du equals 3dx. And now, we notice that, hey, I have this entire thing in my integral, 3dx. And I can substitute that for du. So all of this is gone, and we can replace it with du. And we can replace u with 3x. So this becomes the integral of cosine of u du. Well, what is that? Well, that is sine u plus c, right? Ooh, but we want to go back to the u's, right? We want to go back to the u's. Oh, the x's. We want to go back to the x's, so we want to plug in this. We want to resubstitute. So u was 3x, right? So the answer is sine 3x plus c. And that's how to do this integral. What about this one? Well, wouldn't you do the same thing? Wouldn't you let u equal 3x, take a derivative, you get du dx equals 3, put it in differential form, you get du equals 3dx. Where's 3dx? It's not here. It's not here. But we can make it here. It is a constant. I can do 1/3 times 3 cosine 3x dx. I just made the 3 pop up, but I had to put a 1/3 in front, so it will be 1. But we still have a 3dx here. We can still do this. So this is a 1/3 integral of this. All disappears because of the du. Cosine u du, our answer is similar. It's the same thing, but the 1/3. So it would be 3 times the sine u plus c. Wait, what is u? U is 3x, and that is our answer. That is a method of substitution. U substitution. Let's do another example. Let's say we have the integral of x square root of x, let's see, to the third. No, that's not good. Let's do x squared plus 1 dx. So, does this fit any of our integration rules? Does it fit some power rule? No, we can't reduce this to one whole term with 1 power and both combine. No, we can't do that. I don't see any trig functions. We ran out of methods. We need something. We need u substitute. Well, let's try u substitution. Okay, do we see a composition somewhere? Yeah, the square root and the x squared plus 1. Well, let's let the inside equal u. So u equals x squared plus 1. Well, what is du? We're gonna skip the du dx part and straight go to the differential form. So we're gonna go du equals 2x dx. And I just skipped one step, but this is usually how we do it. We don't bother writing du dx equals 2x multiplied dx on both sides. We usually go from here to here, like that. Okay. Well, can't I just substitute? Wait a second. Do I see a 2x dx anywhere here? I see an x. I see a dx. How do we get the 2? Just put a 1/2 out here. We get the integral of 2x root x squared plus 1 dx. Oh, now we have a 2x dx, right? So let's substitute. So this is 1/2 the integral of what? Well, this stuff disappears because that trades in for du. This stuff disappears and trades in for u. So we just got root u du. Okay, what's the integral of that? Well, it's u to the 3 halves. Sorry. Got that one wrong. U to the 2/3 to the 3 halves. Oh, we're multiplying by 1/2. So that's going to change into a 6 halves, which is what? 1/3, right? Okay. Plus a c. Oh, but wait, we don't want u's on our answers, we want x's on our answers. So we just replace u with what we had with x, right? So this is 1/3 times x squared plus 1 to the 3 halves plus some constant c. And that's how we do the integral. So it's not so hard. Not yet. It gets difficult sometimes. Okay, let's do another one, and I'll do this one on purpose, just for you to recognize, well, what is this? So if we do the integral of x squared, wait, this is like the same kind of problem, right? Oh, wouldn't you say that u equals x plus 1? Du equals dx. Okay, we have a dx, right? Okay. What about that? What do we do? We have too much. We don't have enough. We have too much stuff here. We have x squared dx, so we can't do u substitution. Huh. We can't do it because we don't have all of this gone. Because the problem is this and this. Huh. That's kind of sad. We can't do it. So yeah, we gotta know when we can do it and when we can't. Because there's a point where you're gonna try to substitute things and you shouldn't. Now, after doing this a while, you gotta remember the form. Remember? The integral of f prime of g of x times g prime of x dx equals your f of g of x plus a constant. You gotta remember that this is what you're doing. We have, what is it? There you go. So we have our u substitutes for g of x, and our du equals g of x, g prime of x dx. And what we're doing to this form is saying, well, let's do the integral. Wait, what's u equals g of x, right? Du equals d. Well, we have that. We have g of x, g prime of x dx. Let's substitute that. So we now have f prime of u du. Wait, we know the anti-derivative of a derivative of a function. We know that's f of u, right? What was u in the first place? It was g of x, right? So we replace u with g. Wait, that's the form. That's the general form. Okay. Guess what? You don't have to do any of this. You can just recognize the entire line. I'll show you an example. integral of, let's see, 2x cosine x squared dx. Hey, what's your composition here? The cosine x and the x squared. What do we need? Ooh, we were going to let you use some, but we don't have to do it. We can literally recognize, hey, in the end, what we need is the derivative of the inside. In the end, this is going to disappear, right? This entire thing disappears, traces for du, comes back there, and that disappears. So, this entire thing disappears. Do we have the derivative of g of x in this case, which is x squared? Yeah, it's 2x dx, right? We have this. We have this piece, it's 2x dx. So we can literally just remove that. And write, well, what's the antiderivative of f? Well, the antiderivative of cosine is sine, right? And leave the g of x alone. Plus a that's it. That's all it is. That's all it is. You have to have the derivative of the inside in order to get this. So when we didn't have if we don't have an x or 2x, we said, well, what do we need for the derivative? 2x. Is it here? No. Well, let's make it there. Let's make it 1/2 or 2, and then this will end up being 1/2. So, it's either you make it into what this is, or it's not even close to being there at all. That's what this form is saying. Saying use substitution is just a bridge. You can just jump over that bridge anytime. You don't have to do the use. They're just there to help you. And after you do it for a while, you don't even have to do it. In fact, you don't even have to do it right now. You can just still, I'm telling you how to recognize the pattern. I'm telling you that, hey, if you find the g of x plus x squared, the derivative of that is inside there. Oh, times dx. Well, I can just do that very easily now. So, that's our example. Okay, let's do another one. The integral... Oh, ouch. Sorry. The integral of tangent of x squared secant squared x dx. These are a special class of integrals, or special technique of the composition, but it's all one thing. It's the same thing. Okay. How do we do this integral? Well, remember this form. Remember that we want to see this form. We want to see it. How do we see? Well, it's this squared. It's the tangent in the x squared, or the u squared composition. I see a square and a tangent as a composition. The f in this case is, or the f prime in this case is whatever you have squared. G of x is tangent. Well, do we have the derivative of tangent here? What's the derivative of tangent? Secant squared x. Oh, it's in here. So we don't have to worry about it. So this is, well, okay. So what's the antiderivative of something squared? Well, it's that something to the third power over 3, right? Remember when we did u over... Well, we just have the tangent inside that u, right? There you go. That's it. And then you put a plus c. See, you don't have to worry about this because it's the derivative of the n side. The tangent to the third over 3 is the result of integrating this chain rule kind of thing, right? This composition derivative. Let's do another one. Let's do another trig line. Helps doing trig lines. So if we have sine of pi x cosine of pi x dx, and you're looking at this, and you're trying to look for this pattern, and this one's special because you can actually do it. They both work. What's my composition? Well, it's the This one's very difficult. The reason why this is difficult is it's hard to recognize your composition. Your composition is sine of pi x to the first power. And the reason why is because you want to really get rid of this cosine. Or you want to get rid of this sine. You want to get rid of it because you can't integrate by separating those. You can't separate those. You gotta get rid of one. How do you do that? Well, you force a composition. You say, well, sine of the first power, well, what's the derivative of sine of pi x? It's the cosine of pi x times pi. Do we have the cosine of pi x times pi? We have the cosine of pi x. We have the hardest part. We just need the pi. We can do that. That's easy. So that's we can multiply pi. In fact, I'll just do it right now. I'm just there's a pi x here. There you go. So we have a pi now. We have a cosine pi x. We have pi cosine pi x. This is the derivative of the inside. Oh, what is that equal to? We'll just get rid of this because this is all gone anyways. So 1 over pi. That's gonna stay there. Times what? Well, we have to keep the inside the same. Because remember, the result of this is just f of g of x. So what's the antiderivative of our something to the first power? Just u. Well, it's that u squared over 2. Right? And we could kind of put there, the pi there. And that's our answer. That's how you do it. That's how you utilize this composition type of thing and integrating stuff. This technique is so well. You can integrate lots of more stuff with this technique. In the next part, you're going to learn about a harder technique that uses substitution, and you have to substitute. But we won't do that until later, like a little bit later. It's a little trick. It's not a big technique, it's just a trick. So that is it. I'll get some problems on the board. Okay, so try these problems. Be careful of these two, especially the bottom one. And that's all the problems I'm going to give you.